Today we're having a look at work, energy and power. Fairly easy sort of concepts. Most of them met earlier in GCSE, and we're going to extend them just a little bit, and we're going to look at a few little experiments to try and make some of this perhaps a little bit clearer. So let's start with some definitions, some ideas of what things are. So if we start with something simple like work, so we can say that work is simply going to be the force that I'm going to exert times the distance moved, and we'll write that as W equals some sort of force times a distance. We'll give it the symbol X here. And when we try to do something, basically we can say that the work done is going to equal the amount of energy that's actually transferred. Now, that's not really surprising. Energy here is defined as the capacity to do work. So we can have a go at looking at a couple of ways of looking at this. I've got over here a few different experiments looking at different sorts of work. We've got the work involved in trying to lift a mass, and if we want to, we can take our mass and we can either lift it up or down an inclined plane. Now, instead of using heavy masses, we can use perhaps lighter masses, and we can pull these up and we can work out the amount of work that's been done on these. So let's start by having a look at trying to move an object and see what we can do with this. So our first one is, well, let's try just moving an object in a downward direction. So let's have an object, and what we can do is we can drop this object to the ground. Now, as we drop this object towards the ground, we're going to have an acceleration. So we're going to bring in all our bits of information we need to know, which is my Suvat equation. We can work out the distance we're going to fall. We can work out our initial velocity. We can work out our final velocity. We know our acceleration due to gravity, and we can work out the time taken. And what this is going to do, it's going to convert potential energy that we have in a system as we turn it to kinetic energy as it falls down. So if we take the fall by gravity machine, this has a height of 0.5 meters, and if we drop this, we can do the timing. We can actually work out the time taken to drop this ball. Well, if I know that, then it's possible to work out what V is going to be. We've got various equations. We have S equals ut plus a half at squared. No help there, because what we want is to work out the velocity. I do know my acceleration is my velocity, my final velocity minus my initial velocity divided by the time. So we could rearrange this one and work out what this is going to be. And this is probably one of the easiest ways. We know, in fact, that u is going to be 0. So if we know that acceleration equals the velocity divided by the time, then we can work out my velocity is the acceleration times the time. So we can work out what my final velocity is quite easily. And once I know some of these things, we can work out forces, we can work out all types of bits, manners and things to work out what we're doing. So we can work out exactly what's going on. So we can drop an object, we can work out how fast it's going when it collides with at the bottom. From that we can work out our kinetic energy, we can work out our potential energy. So let's start with this experiment. So my gravitational potential energy is going to be the mass times the gravity times the height. My mass and gravity here is the weight of my object, and the height we know as our distance, s, 0.5. When I drop that, it becomes equal to the kinetic energy, which we know is a half mv squared. So if these are equal, I know that mgh equals a half mv squared. Well, I've got m's on both sides, so I can cancel that out. And we can work out from here everything that we need to. What we're going to do initially is let's work out what our kinetic energy is, and we're going to work that out by recording the mass of the ball bearing, which we're going to do very approximately with a pair of scales, and we're going to work out its velocity as it falls. So I've got this basic setup. We've seen this before in another video. I'm just going to move it along to upset my son. And what we're going to do is we're going to ensure that this is running the right program, and hopefully when I put this ball in, it's going to release and we're going to get a time. So let's do this. I get a good run and the time is 0.343 of a second. That sounds quite reasonable. We'll repeat it a couple of times. So we had 343, missed, it decided that took a long time, reset itself. Let's try again. It didn't like that one. Much better, and we get reading it 343. So let's take that as my distance we're going to fall and my time, 0.343. We're going to want a balance now to record the mass of this. It's a little bit lethal around here. Let's see what we can do. 24 grams. Right, so let's go back to what we had. We've got then a time, and that was 0.343 seconds, and we know the mass is 24 grams. So this will enable us to work out everything we want to do our equations. So we're going to use this idea. My velocity is going to be the acceleration, which is 9.8, times my time, which is 0.343 of a second. Let's just put that into the calculator and work out the answer. So let's go for 9.8 times 0.343, and that's going to give me a velocity here of 3.36 meters per second, finally when it hits the ground. That we can relate with our kinetic energy, equaling a half the mass. Now 24 grams then is going to be 0.024 for kilogram times 3.36 squared, half mv squared. So we can work out, going to the calculator, what that's going to be. So what I'm going to do is, once I've found where I put the mouse, it's going to be that number, it's going to be that number squared times 0.024 and times that by a half. And that gives me the kinetic energy, which is about 0.135. If we compare that with our gravitational potential energy, what we started with, our gravitational potential energy, this is going to be our mass, 0.024, times the force of gravity, which is G, which is 9.8, and this is then going to be multiplied by the height, which is 0.5 of a meter. And we'll see how well we come out here. So let's go over to the calculator and work this one out. So we've got 0.024 times 9.8 times the mass. Oh, we've done the mass. We've got the distance, which is 0.5 of a meter. And that's going to give me a number about the same. It's not quite, but then I'm using some Lego and it's not necessarily very accurate, so the mass of the scales is the same in both cases, so it should be the same error. So they're approximately equal to one another, which is what we'd expect. We would possibly expect the kinetic energy to be slightly lower. So we've got this idea of something falling. So it's managed to make some sort of work. It's done some work as it's fallen. How about if we try to take this mass and move it up an inclined plane? So what I have here is an inclined plane and a ball bearing that's going all over the place. Now, with this inclined plane, it's got a measurement on it. I had a look at this and I didn't think it looked brilliant. The scale didn't seem to start at the bottom or the top, so I wasn't that impressed. So what I did, I tried two things. The first is I got my mobile phone out, and the obvious thing with my mobile phone is to put the inclinometer on there, and if I set the inclinometer up, it reads 35 degrees. It's having a hard time here. I worked hard, I set it up at 35 degrees. Since I didn't believe that, I laid it down and I measured the angles exactly, and it came out here 35 degrees. So I now know that this is at 35 degrees. So what do we now need to try and do? Well, if we have a question, and the question is about an object being moved up a block, well, we need to perhaps work out something about this mass. So let's take a mass here, and this mass is 769 grams. I don't know why they chose that particular mass, but that's what we've got. I've just recorded that mass, and what we can do is we can take this mass and we can do some work on it. What I can do is I can take this and we can move it up a slope. Well, what do we need to know for this object to do this? Well, I need to know the force that I'm applying on it, and I also need to know the distance it's being moved. So the first one I can easily remedy, that this is 60 centimeters long, but how far is my object going to move along there? Well, that's a different question. So what we can do is decide on where we're moving it up to, and I can only move it up so far. So what we can do is we can work out how far this object is going to go. So let's measure this distance from keeping this hand flat against there, so I know where it's going to go, and that is then going to move up. I've moved it. Let's do it again. And we can move that mass up here, and I think if we set this up to a point about here, it's going to be 40 centimeters. So what I'm going to do is I'm going to mark that point on here with my pencil. So I now know that distance it's going to travel is 40 centimeters. Well, what we're also going to need with this is some idea of the force that's going to go up here. If I want to lift this mass vertically, then what I've got to do is to lift this vertically. If this weighs 760 odd grams, then to balance it I would have to put in a force here on this side of the same. So we've got to put the force in of this mass times gravity. But as I pull it up this slope, this inclined plane, hopefully it's going to get easier. So let's do a quick comparison. I've got an 800 gram mass here. I've got my 760 gram mass here, and if I put on this mass they should find that this one is just slightly heavier and it's pulling it down. These now actually move quite easily because there's not much difference. There's only about 40 grams of weight difference in them. I do have that hanging in the way. Let's just move it out of the way for the time being. So this one is slightly heavier. Let's take one off. Now, obviously, it's lighter. Let's put it on the inclined plane. And now that force of the 700 grams here times gravity is more than enough to pull this up. Let's take one off. And it's still just enough to pull this up. We can look at what force I've got on here, going down, to pull this through 40 centimeters distance. It is going, it will get there. So the other mass falling down slowly, pulling this one up. We're now pulling also against friction, but you can see the point of the inclined plane. There we are, it's moved it through here 40 centimeters. We can calculate this just as easily. Let's have a look. I've got my mass, which is here 769 grams. We know it's being pulled up a slope, and this slope we've measured carefully to be 35 degrees. So I've now got my mass here moving up the slope, going over the so-called frictionless pulley, and any of you who do A-level maths will find this experiment reasonably familiar. And going down here, I've got another force here of, this time it was 600 grams, times by my 9.8. If we look at what we're doing here, my work done isn't simply my force times my distance, because the force, we're looking at some sort of relationship here with the force and the angle. We know that we've got this going up in this direction, so we've got a little triangle. We know this is 35 degrees. We can measure this to work out what components of our vertical and horizontal forces we've got, because we've got a vertical force and we've got a horizontal force, which is making my object move up here in this direction. I suppose another way of looking at this one, we could actually look at that force being sort of going up, because it is really going up because it's pulling in that direction. It's just we're using the pulley here to pull it in the other direction. So we can now work out where the force is applied at an angle to work out what's going on. And if we take our normal right angle triangle, then if I have got my force, which is my hypotenuse, then we can work out what the forces going in the other way are, because I can either work out the adjacent, which is going to be the cos, or I can work out the opposite here, which is going to be the sine. So we can work out which way our forces are being applied to work out any of these values. So we can work out, for instance, in a slightly different way, if I've got a block being pushed along the ground, here I'm pushing at a force here, let's suppose it's 35 degrees again, to the angle, there's my force, then I'm trying to look for this particular direction, not the up and down, but the along. So this would mean that my work here would be my force times the cos of my angle, which is, in this case, is 35, times by my direction of motion, which here we could call x. So we've got ways of trying to work out what we're doing here. Now, I haven't taken all the readings here to actually do what I want to do, and it's just an approximation there to work out what's going on, to try and show you that if we're pulling an object vertically and we're doing it at an angle, then less energy is required on the inclined plane. Which brings me to something that I see a lot. I've been watching a little program on TV. I've been watching Snowpiercer, and I was interested to see the train was driven by a perpetual motion engine. I think the science fiction writers may have sort of not attended school and didn't perhaps know what perpetual motion was. We have the conservation of energy, and we've looked at this in a previous video of having two objects collide with one another. So if I have my two trolleys and I have one moving at 4 meters per second and the other one stationary at 0 meters per second, when they collide, they're going to both move off, assuming the same mass here, at 2 meters per second. We have conservation of momentum, we have conservation of energy. Conservation of energy simply means that energy isn't going to be created or destroyed. If I put X amount of energy into a system, then I can expect to get X amount of energy out of the system. They won't necessarily be the same, as in we may find that we've converted one sort of energy to several others. There might be here friction involved, there might be something like sound involved, but if we add all those up, they make that value, X. And that is this idea of conservation of energy. So let's suppose I start off with a little machine, and let's make this little machine have some little masses on it. Now, I've seen these ones where they retract the mass on this side and they extend the mass on this side. This makes this side heavier than that side and it moves down. And as it does so, these masses are then brought inside, only to be put outside when they come round the other side, and so this supplies energy because this side is heavier, and so my machine will move forever. And if it's set up really well, it should more or less run forever. But we've got an enemy. We've got friction, and when I listen to this I can also usually hear sound, and we're losing this energy as friction and sound, and so slowly this item is going to stop. But perpetual motion machines are worse than that. They expect this to be spun round, and I can then take out some energy from it, and this will still carry on at the same speed. Obviously, energy is being supplied to this from nowhere, and if it's not being supplied by anywhere, well, where do you expect to get the energy from? It does worry me when I see people who make these wonderful machines and they seem to think that they can make energy from nothing, and it's a big problem. So we've got a whole variety of forms of energy. Perpetual motion, it's out because it will violate this idea of the conservation of energy, that energy will be somehow constantly put into this machine. We've looked at kinetic energy, energy of motion. We've mentioned gravitational potential energy, the energy of position in a gravitational field. We've got probably one of my favourites, which is chemical energy, the energy contained within chemical bonds. We've got elastic potential energy, where we can store energy up in a spring or elastic band. We've got electrical energy, electrical potential energy here, because the energy of electrical charges due to their position in an electric field. I've got nuclear energy, the energy held up inside an atom. I've got what I will term electromagnetic energy, the energy associated with all the electromagnetic waves that might actually still be stored up in an oscillating electric magnetic fields. I've got sound energy, the energy of mechanical waves, this energy of compression of atoms. And we've got this idea of internal energy of an atom, the sum of the random potential and kinetic energies in an atom of a system. But regardless of the type of energy, they all follow this principle of the conservation of energy. The fact that we can convert energy from one form to another, and if we've got a closed system, energy can never be created or destroyed. It merely can be turned from one form to another. we've looked then at kinetic energy, this idea of kinetic energy of movement. We can convert stored energy, typically here as gravitational potential energy. My favourite Hot Wheels experiment, where I can take my Hot Wheels car and it can go down and it can loop the loop. Always fascinates me, that fact that the car will actually stay up on the top of the loop. I know why, but it still fascinates me. And we can have the idea of objects colliding with one another and dissipating their energy into different forms, being buckled, deformed, changed. So we've got kinetic energy, this idea of energy of movement. Sorry about that. We have gravitational potential energy, the energy of acceleration due to free fall of gravity, the idea that we can, as we lift something up, then it can gradually fall down and accelerate. So I've got my object that will fall to Earth. Brilliant idea. I'm glad, so glad really, that Newton managed to sort of sit under that apple tree and work out what was going on. Because without that, we wouldn't have things like roller coasters, and this idea that we can start at the top of a roller coaster and we can go down and then we can nearly get as high again, energy loss to sound and friction, and we can come down, we can roll up again before we manage to finish up where we started. Energy, of course, had to be added to the system so that it could be lost along here. And we can make some of the most wonderful roller coasters. And if you like roller coasters, then you can have a look at some of the videos I've created on this to look at the energy changes in roller coasters as we sort of add energy to systems and then we lose the energy as it returns. And these systems are the same for electrical and other types of energy, and we can use these roller coasters as a simulator for some of the others. And I'll get my son to put a link in so we can actually see this in the description. So we've managed to create some energy, generally by doing things like chemical work. I've got to try and get this rubber up here. How do I get this rubber up here? Well, I used chemical energy to actually get it here, and then that chemical energy can be turned into sound energy and kinetic energy, and probably some heat energy as well. And everything usually ends up as heat. So we've got some various ideas there of energy and work. Our basic energy rules we have to remember: energy cannot be created, it cannot be destroyed. All we can do is move things around. We can observe how these things go with force and distance graphs to try and work out how things sort of relate. You've probably all done the Hooke's experiment, Hooke's law experiment, where we can also put in a force, and we can measure here the extension, and we'll see for many objects this represents a straight line. Here we know we've got a half F and the change here in length for what we're trying to do. So this here, this delta L, represents the work done to stretch a spring to have this amount of extension, the change in length. We've got kinetic energy. We have our ways of trying to work out what's going on, but we can relate some of these to our equation, F equals mass times acceleration. But I also managed to work out earlier that my acceleration is my change in velocity with time. It's just now, if my velocity was 0 here, it's just going to be that. So if I now know what A is, I can say from that that my force is going to be my mass times the velocity divided by the time. So we know that work equals force times distance. We know it's also going to equal to mv over t. And we can work out from that a variety of other things, like, well, I've got my distance. What's my distance? I know there's my force. How could I work out my distance? Well, that's going to be my velocity times my time here divided by 2. And if we put that together, it gives us a half m v squared. The t's cancel out. And there's my kinetic energy. We know they change, they move from one to the other. So we can work out the movement of all sorts of fairground machines. We can work out the energy required simply to raise my mass by the force I pull down on this. So I can actually work out what this is going to be. So if I've got here a weight of 200 newtons, and then if I raise this by 1 meter in 2 seconds, we can work out my power, because what is my power? Well, my power is simply going to be my change in energy in the time taken, delta E over delta T. My power here is my work. Better to do this one as I change in here work done per second. So we can work out how all of these bits and pieces work together. We've looked then at some ideas of work, of energy, of power. I hope they found some of those things useful, some insights in how things work, and if you like what you just saw, then please subscribe and I'll see you next week when we'll do some more A-level physics topic by topic. Bye bye.